Hello and good evening, everyone. My name is Hasib, and today I will be presenting the project. So our project name is World Model for Unconstrained Goal Navigation. Now, what is a goal-conditioned reinforcement learning? A GCRL is a framework where the agent receives different goal commands. So in a GCRL, the agent has one policy to reach many different goals. Now, some sparse rewards are a problem. Dense rewards can have many problems, such as domain expertise, you need access of object positions, and it can be time-consuming when you're manually designing the problem, and also it is very error prone. So the GCRL uses sparse rewards which can reach the goal, and it leads to poor exploration. How the world model helps in this one. So the world model can help with the poor exploration by giving rich training signals, and it allows the agent to imagine future states. So it enables planes without interacting with the real environment, encouraging efficient exploration. Furthermore, there are limitations to current world models. What are the problems or the limitations? The problems are that model generalizes only around recorded forward trajectories. It fails to generalize backwards or across different trajectories. This motivates improved data richness and transition coverage. Now, there's a problem setup. We use the Markov decision process, which has a state space, action space, goal space, and the rest of the following. And the assumption in the paper is that the goal space is the same as the state space. Now, if the goal condition is met, then the policy learns to use the same policy to find different goals. And the reinforcement learning objective is to optimize the policy in such a way that it uses the same policy to reach different goals. Okay, the model-based reinforcement learning framework uses the M-hat, which is trained on trajectories from the replay buffer. Now, the actor and critic are trained using imagined rollouts. This improves sample efficiency and exploration. So the most important thing in this model is the replay buffer quality, because replay buffer usually contains limited paths and it can only have forward dynamics, and many valid transitions are missing. So this motivates the need for a method that encourages diverse transitions. It enables transitions between subgoals, and it improves world model generalization. So the problem summary is, the core problem is that the current world model learns from limited trajectories, and we have to solve that issue by implementing richer replay buffers, better modeling of arbitrary state transitions, and a way to discover key sub-goal states in tasks. This leads to the method proposed in the paper, which is the MUN. Now I'll pass my turn to my member. Thank you very much.
So now I'm going to talk about the methodology part for this paper, which is all about the algorithm of this MUN, which is World Model for Unconstrained Goal Navigation. And this covers two subsections, which is training generalizable world model and also generate key subgoals through distinct action discovery DAD. So the core challenges to be addressed in goal constrained reinforcement learning is the efficient exploration in long horizon sparse reward environments. And the purpose of this algorithm is to enhance the agent's understanding of the real world environment through dynamic or world modeling and latent space representation. And the expected outcome is to boost real world performance by enhancing the world model's quality. Enable effective goal orientation exploration as the world model generalized is also an outcome. So this is the workflow of training the world model. So the world model is trained on the agent's past experience from the replay buffer. And the replay buffer consists of observed environment transition, linking the past and future states and the corresponding control actions. So through supervised learning, it generalizes well when forward along trajectories and generalizes backwards or across the trajectories. So compared to unidirectional buffer, bidirectional buffer covers wider observation space and also richer dynamic transition. So this created more reliable latent space and also use higher quality reward function. At the end, the policies are more generalizable to the real environment. So this is the algorithm. This figure shows the framework or algorithm of MUN, and the whole workflow is to update subgoals, collect data, build bidirectional buffer, which can store bidirectional subgoals transition, and also train world model using both new buffer and original buffer, and also use the train world model to generate imaginary rollouts. And this is the comparison with GoExplore using MUN. So the strategy is to change the original goal phase and explore phase into two goal phase. And the overall efficiency is MUN is computationally efficient compared to GoExplore. So this is the next section, which is to generate key subgoals using DAD. And the challenge is that we need to find the pivotal subgoals. And the most straightforward approach is to simply selecting at fixed time intervals. So, and the solution in this paper that mentioned to improve the naive approach is with this DAD, a method which can automatically find the essential pivotal subgoals. And the core insight is that there exists method to find key subgoals, but all of them tend to be overly complex and not generalized. And they also found that key subgoals almost always occur right before the distinct key actions. And this is the DAD algorithm, which is a simple and efficient method. It can identify distinct action and extract the corresponding states as the key subgoals. And also The mechanism inside this algorithm is the farthest point sampling, a simple and efficient approach to select n states that have the most distinct action. Now I will pass it to my next member. Thank you.
Right, so now we'll talk about the experiments that were conducted across 6 challenging goal conditional tasks in robotic manipulation and also navigation environments. So specifically in M-maze, and then the second one, Walker, the 3-box staking, the pen and block rotation, and also the last one, flashlight. So all of these experiments was to address the 3 research question, which is, does MUN outperform other goal conditional model-based reinforcement learning baselines with advanced exploration strategies? And also, can they effectively identify key sub-goal states along trajectories to the environment goal region? And also the third one, does MUN successfully leverage the bidirectional replay buffer to train a generalizable policy for navigating effectively between arbitrary subgoals? Right, so the next. So the first one is the M-maze. So this experiment requires complex 4-leg locomotion to navigate a maze. And then the second one is a walker. So walker means that 2D robot learning stable, walking on a flat plane. And then the third one is the 3-box staking. So in this experiment, so a robotic arm must stack 3 blocks into a tower and then a pen and also block rotation. So these 2 tasks require an anthropomorphic robotic hand to manipulate objects to achieve specific rotation. And then also the last one, flashlight. So in this experiment, a manipulator will slide a puck to a goal location on a slippery table. So then I will now talk about the result of the experiment and also the impact. So from here, we can see the result. So we can find that MUN demonstrates superior efficiency in training generalizable goal condition policies compared to other baseline methods and also ablations. So in some highly challenging tasks, such as the 3-box staking, block rotation, and also the pen rotation, so MUN show a significant performance margin. So for example, we can see here the 3-block staking. The MUN achieved over 95% the success rate on 3-box staking, whereas other baselines only reach around 60% within 2.5 million steps. So the goal explore strategies, PAC-G and also MEGA-G, sometimes result in a suboptimal goals, but it will potentially slowing down their exploration. While GC Dreamer lacks a goal explore phase, so which limits its exploration potential. But sometimes we can see that here the GC Dreamer can still perform better than MEGA-G and also PAC-G in certain contexts. So this shows that the goal explore strategy does not always guarantee improved exploration, and also suboptimal goal setting during the goal phase can hinder exploration. So we can see the GC Dreamer can sometimes outperform than PAC-G and also MEGA-G baselines. So, and also the MUN achieved the lowest one-step prediction error and also maintain the lowest compound prediction error across all the 6 types at here. So we can also find the result of the additional experiments at here. So we can see the MUN outperform all the ablation and also the baselines at here with the highest success rate. So from here we can see the impact. So the MUN is capable to develop a robust and also adaptable world model, okay, and of learning states transition between any arbitrary states in a replay buffer, including reverse complex process like unstacking the block. So the DAD strategy was effective in identifying key subgoals that represent pivotal milestones necessary for task completion. And then MUN outperformed all the ablated versions such as the MUN NS-3, MUN -no DAD, and also MUN keys OBS. So at here we can see that MUN is can develop as a world model, and it will enable the model to accurately represent the transition from moving backward along recorded trajectories and also the transition between states across different trajectories. So that's all from me. Thank you.
Hi, I'm Zephram, and I'll be concluding this presentation. So this research paper has shown us that MUN is a new goal-directed exploration algorithm that is designed to improve world modeling. The paper also introduces DAD, Distinct Action Discovery, which is a practical strategy for identifying important sub-goal states that serve as key milestones in solving complex tasks. And after some experiments, we see that MUN significantly enhances world model reliability, and it also learns policies that generalize well to new task goals. But with all the good things, there's also its limitations, which is that the MUN approach depends heavily on efficient sub-goal discovery strategy. So the DAD performs well in general, but in environments that are complex, which has like large action spaces or like a weak correlation between actions and goals, it will tend to fail, and it tends to identify irrelevant or ineffective sub-goals. Essentially, the MUN's current performance is limited by the quality of sub-goals and the system's ability to autonomously navigate between them. That leads us to future works where we can improve these limitations, and one of them being to build a stronger self-supervised sub-goal discovery method. So some examples we can do or use is the constructive representation learning, which helps identify which states are similar or different, and then it groups those meaningful goal-related states together. And another one would be graph-based sub-goal extraction. So these two sort of help focus on making the MUN smarter at automatically choosing which states matter, especially in noisy environments. And the next one is to extend the MUN beyond just a model-based method and to a model-free reinforcement learning method, because this model-free method is much more simpler and it doesn't learn from a world model. It directly learns policies from real trajectories. An example of this would be to integrate MUN with soft action critique and hindsight experience replay. So this combination of SAC and HER already helps the agent to learn from sparse rewards. By adding MUN on top of that, it sort of provides more meaningful sub-goals, and then that will guide the agent during training, and thus leading to better exploration and faster training. All of this without a world model. And to end things off, I would share an insight that I've gathered, which is that sub-goal discovery is not just helpful, it is really essential for world model reliability. Many reinforcement learning papers out there, they treat sub-goal as sort of just a navigation help, but this paper really shows how important it is. Poorly chosen sub-goals will lead to poor exploratory transitions and thus a weak world model. But then if you choose a good sub-goal, you get richer, more diverse trajectories and a really robust and generalizable world model. And the world model quality itself depends heavily on what states the agent choose to treat as sub-goals. So good exploration doesn't just help the policy, it directly shapes the whole structure and accuracy of the learn world model. And that is all from us. Thank you.